Okay, in this example we have a function with 3 inputs and 1 output. That means, let's see, if we think about this one output maybe as being W, we can talk about the change in W, or we could call the output F and call it dF. But anyway, it's going to have to be a 1 by 3 matrix. 1 row because there's 1 output, and 3 columns because there are 3 inputs. Now, in each of these we just do the first entry is going to multiply the change in x, so it should be the derivative with respect to x. The second entry is going to multiply the change in y, and the third entry is going to multiply the change in z. So it's going to have to be the third entry is going to have to be the partial derivative with respect to z. So let's see, the derivative with respect to x is y squared z cubed, and the derivative with respect to y is 2xy z cubed, and the derivative with respect to z is 3xy squared z squared. So one application here was if we had particular values of x, y, and z, then we could calculate the slopes here, and then we could think about, okay, what would happen if I made a certain change in x, or a change in y, or a change in z? This, we could multiply it out, and that would give us the change in the output. Another example, another thing we could do with this is to calculate the linearization. So let's find the tangent space. Let's see, so the tangent space at, let's give a value for x, y, and z. How about 2, negative 3, and 1 for x, y, and z? In that case, then f of 2, negative 3, and 1 is 2 times 9 times 1 would be 18. So the change in f, that would be f, or w minus 18, right, is going to be these rates of change. The rates of change that we have, let's see, at when y is negative 3 and z is 1, negative 3 squared is 9 times 1 is 9. And if we take 2 times negative 3, that's negative 6, times 1 cubed is 1, so 2 times negative 6, that's negative 12. And at 2, negative 3, 1, let's see, 3 times 2 is 6, times 9, 6 times 9 is 54, times 1, okay, so 54, times the changes in x. How far does x move from 2? How far does y move from negative 3? Y minus minus 3 is y plus 3. And how far does z move away from 1? Then we get this linear function, w equals 18, or let's see, 9 times x minus 2 minus 12 times y plus 3 plus 54 times z minus 1 plus the 18. I had w minus 18. I brought the 18 over to this side, so I have a linear equation for w. So if we had this original nonlinear equation for w, now we have this linear equation for w. Let's see. If I multiply out, I have a 9x and a minus 12y and a 54z. And then for constants, I have a negative 18. And negative 12 times 3 would be negative 36. And 54 times negative 1 would be negative 54, plus 18 here. So the 18s cancel. So this whole constant then, let's see, negative 54, negative 60, negative 90. So there's our linearization, 9x minus 12y plus 54z. How could we visualize or compare the linearization to the actual function? One way to do that, since this function has 3 inputs and 1 outputs, the visualization we usually use is to look at level sets of this function. So we could look at the level set of this function when w equals 18, and then we could also look at the level set of this function when w equals 18. Let's use Maple to visualize that. So let's see, we've got here, in order to look at a level set, probably be easiest for us to use implicit plot. So we'll do implicit plot 3D, okay, and then for the nonlinear function, we're talking about the level set when w equals 18, and that's 18 equals x times y squared times z cubed. So 18 equals x times y squared times z cubed. And that's our, and we're looking around the region where x is 2, y is negative 3, and z is 1. So let's let x equal 1 to 3, and y equal -4 to -2, so that contains -3. Let's see, z equals 1, so let's do z equals 1, 0 to 2 would be a nice interval containing that. I'll call that my first plot, so that's P1. And I also want to plot the level set for the linearization, or the tangent space, in that same region, right? But the linearization is, let's see, if w is 18, we have 9x minus 12y plus 54z. 9 times x minus 12 times y plus 54z times z minus 90. So there's the equation of our linearization. Let's display both plots together. So we'll display P1 and P2 together here. Oh, nice. Okay, so we use implicit plot. We got, you can see the nonlinear one is bending away, right? So that's the level set of the nonlinear function at w equals 18. And in that same location, we have the level set of the linearization is a nice flat approximation, simple linear approximation to that nonlinear function. And it's pretty cool how the linearization is always just a simplification of that original function. It all comes from this total derivative matrix, which just contains the rates of change of the function in various directions, right? So there's one row for each output, and there's a column to contain the rate of change in each direction of the input. So partials with respect to x, partials with respect to y, and partials with respect to z.